Okay, we're back. I didn't know we only could record 10 minutes at a time with this tool. That's fine. All right, so we were just finishing up the part of the review that was about vertical structure of the atmosphere. You really just need to know the last one that we were talking about right as we got cut off was the thermosphere. After that, there was something about the homosphere and the heterosphere, which is a way of sorting out the layers of the atmosphere based on the chemical composition of those layers. You don't need to worry about that. Heterosphere and homosphere are not on the test. All right. So as we move on from there, we got to the lecture that everybody hated, that two-part thing about heat in the atmosphere. Now, I know some people had a trouble viewing it as a PowerPoint. I know the link worked for the video, but some people had a trouble if they wanted to get to the PowerPoint. So I've also added them there as a Google slideshow, which I know sometimes works better for people. So let me just real quick go through part one of this and make sure that the most important things that we are going to be talking about actually are what I'm pointing you to here. First of all, you definitely need to know this business about three ways to move heat in the atmosphere: conduction, convection, and radiation. Convection and advection are sort of the same sort of thing. Convection is when you're moving heat up and down, and advection is when you're moving it horizontally. Conduction, remember, is when you're moving heat between two objects that are touching and have different temperatures, like these eggs and touching the hot pan here. As it turns out, air is terrible at that. That's not a great way to do it. In fact, really the only way conduction comes into play in the atmosphere is that the ground warms up from the sun and then the ground conducts heat into the atmosphere. But even then, that's kind of a hard way to go. Looking at our list again, the second choice was convection. Convection is when you move heat by moving fluid that has been warmed, like warm air rising over a fire, or these hot air balloons rising up off this field over here, or whatever. A pot of hot water bubbling up, and the warm water from the bottom rising and cooler water sinking. Those are all good examples of convection. The word advection, I don't think appears on your test as a separate idea. And then we had some examples of those questions. Again, I can't emphasize enough convection, these questions being a really good way of trying to figure out if you're ready for the test. The big part of this section, though, was about radiation. Radiation is transferring heat in the form of waves in the electromagnetic field between objects that are not touching. And this is how, like, heat comes from the sun to the earth, or how heat moves through the Earth's atmosphere, or how different kinds of energy or photons are transferred through the Earth's atmosphere. We often use that word photon, but only when we're talking about the type of radiation that we call visible light or maybe ultraviolet light. There's lots of different kinds of radiation: infrared or long wave radiation and microwave radiation. The only way these are different has to do with the wavelength of the radiation. That's a rather difficult physical concept. We're not going to get too bogged down about how these different types of radiation are related, but it is important to understand that everything on Earth, everything in the universe emits radiation all the time. It's part of what it means to be matter. The only thing that is different from what kind of radiation a star is giving off and what kind of radiation you're giving off is determined by these two radiation laws. One was the Stefan Boltzmann law that says that the amount of radiation that's being emitted by an object is determined by its temperature. So a hotter object like the sun will give off more radiation per square meter than, say, you will give off, just because your temperature is much lower. The other important radiation law was this Wien's law that said that hotter objects emit mostly shortwave radiation, and like visible light, which is why we have visible light, right? The sun is hot, it gives off shortwave radiation, and cooler objects, like things that are at the temperature of the Earth, like terrestrial objects, will emit long wave radiation, like infrared radiation and microwave radiation. And so from the point of view of the atmosphere, there were these two different streams of radiation. There's shortwave radiation coming from the sun, and there's long-wave radiation coming from things like the ground, the atmosphere, clouds, and so on. Giving off radiation is an important tool, giving off to result in cooling of the object. When objects give off radiation, they cool. So like when a cloud emits some radiation, or at night, like in this camping scene here, when the ground is emitting radiation, it cools off. That's part of what happens at night, is the ground is cooling because it's emitting radiation. On the other hand, objects, when they absorb radiation, they warm up. Like, for example, the ground is in the sunshine in this little black and white picture here, and it got very hot. In fact, that kid is frying an egg on the ground. This is an important idea, this business of emitting and absorbing radiation. Everything is always emitting radiation, and everything is always, radiation is hitting it. It might be absorbed, but it might be reflected, it might be transmitted, that means to go through the object, or the radiation might be scattered. Absorbed, remember, is how you heat something up. When an object absorbs the radiation that hits it, the temperature heats up, like this parking lot or the food inside of this microwave oven. When it absorbs the radiation, it warms up. When radiation is reflected, like light radiation being reflected off that mirror or light being reflected off that bright white snow, it doesn't change the temperature of what it is reflecting off of, and therefore it isn't part of the story of warming or cooling the object. Hey, by the way, there was a key vocabulary word that certainly does appear on your test, and that's albedo. Albedo is the fraction of all the shortwave radiation, that is to say, the solar radiation that is being reflected by the object. It's a number between 0 and 1. If it's 0, the object is completely black. It's absorbing all the radiation that hits it. If it's 1, it's completely white. It's reflecting all the radiation that hits it. Another possibility is the radiation can be transmitted. It can be moved right through the object without it being absorbed or reflected or anything like that. X-rays from your dental lab go through your gums and things like that. Or sunlight is mostly transmitted through the Earth's atmosphere. Your cell phone's radiation, the signal. My 6-year-old is right here with me. Hi. Is being just the radiation that your cell phone's antenna is giving off towards the cell phone tower is being transmitted through the walls of the building. The other possibility was scattered. Remember, scattered is when the radiation is sent off in a new direction. This was a story about why the sky was blue. This was a story about like why it's hard to see through fog and so on. In fact, do know this business about why the sky is blue, and we'll deal with that. I think there's only maybe 1 or 2 questions on the test, but you do need to review that kind of stuff here. Just walking through here. It might be easier to think about why it's hard to see something on a foggy night and so on. Again, we walk through this whole question there. So now that we know what different kinds of things can happen to radiation when it hits an object, we can start thinking about what that means for Earth's temperature. It's another example of a budget. Remember, budgets are a real theme in this course. Budgets give us a way to keep track of what's going in and what's coming out, and therefore how it should change. Here we're going to make a heat budget for the Earth, keeping track of how much radiation goes in from the sun and how much comes out in the terms of long wave radiation. That's probably a good place for us to pause before this tool cuts us off again. And I will see you in part 3 of this lecture.